Okay, so this is lecture 10 about delay. So, how was your Thanksgiving holidays? So, so now let's go to our previous lecture. So, our previous lecture was lecture 9, and at the time we have talked about CMOS inverter, and we have thought about skewness between N and P. So CMOS inverter has two transistors. One is P MOSFET and one is N MOSFET located here. So VDD, and also we have M MOSFET, P MOSFET, and they are driven by the same input voltage. So input voltage, and their common drain bias or drain voltage is taken as output voltage. So this is the one, and although we know the basic operation of this CMOS inverter, but the ideal one has the input threshold of half VDD. So we can change our input voltage from 0 to VDD, and also the output will vary over 0 to VDD range. And the idealized behavior would be like this, and we wanted to have just half VDD to decide whether the input is regarded as a low value or high value. But unfortunately, if we have unmatched N MOSFET and P MOSFET, then one of them is stronger than the other, so our voltage transfer curve can be skewed. Here, skewed means that something like this or something like that. So I have shown here the real world example. So sorry for this low resolution graph because I took it from my cell phone. So currently we cannot access this site through the PC environment. So it is taken from IDM 2023 press kit. So it means that still we are not open to this information. So this is December. This event will be held in December in San Francisco, and there the company will present this result. So please have a look at first this right figure. So what is it? This is actually the CMOS inverter we have to consider. So please consider why it is a CMOS inverter. Seems to be quite weird, but this is the state of the art. So here we have two silicon channels. For example, here, can you see it clearly? Si, 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 Si. This is silicon, and also you know that here we have silicon. So please regard them as our diffusion area. So it starts from here to there, then there is silicon, and in between, of course, it is here, that is N-type, and this is P-type. You can immediately guess that this will be corresponding to our N MOSFET, because here we have N-type doped region, and here we have P MOSFET because this is a P-type doped region. And you can see that now here we have power supply. So this is corresponding to VDD. So our VDD is connected to here, and here we have, sorry about this once again, this low resolution, but BS con, so backside contact. So VDD is just connected through this way, and eventually you can see that there is the attachment between this p-type region and backside contact. So then I wanted to ask you a question. What is it? What is this part? This part is nothing but the source of our P MOSFET. So are you with me? And here we have another part located here, and although not shown here, this is grounded. Then what is it? This is the source of our MOSFET. So we are now talking about these two parts in our schematic. And here we have, here we have a purple region and blue region. And here, although we have different names like P-type work function metal and N-type work function metal, but both of them are just metals and they are connected to each other. So you can see that there is no dielectric separating them. So you can easily understand this one and this one are connected to each other. What is it? This is actually corresponding to our input voltage. Then what is the remaining thing? The remaining thing is the drain. Where can you find the drain? Can you point out? The drain can be found in this part and that part. Oh, by the way, drain of MOSFET and drain of PMOSFET, they should be connected. Then where can you find the connection between these two parts? So actually you can see that also here we have another yellow region corresponding to a metal. So simply speaking, although quite complicated in its drawing, but this is nothing but just a realization of a CMOS inverter. So are you with me? So I wanted to say that this is a really new approach to build a CMOS inverter in a small footprint. So usually up to now we must draw MOSFET and PMOSFET separately in our layout, but in this new technology we can just overlap them all. Then roughly speaking, we can reduce the spend area, consumed area by factor of 2, because previously there was 2 separate MOSFET and PMOSFET and they are overlapped now. Okay, so however, the reason why I'm showing this figure is not for this brand new technology, but please have a look at the left hand side figure. This is taken from their press kit information, and now you can see that here we have values like 1 and 1.22. So if we have to say this is really well matched, then we have to expand it to 1.22 volt. You know that if we say so, I mean that in this case VCC is 1.25 volt, and VCC here, VCC means that nothing but just another name for VDD. So just to treat it as a VDD. Then please have a look at this lead curve. Lead curve is easy to see. Then my question is it well balanced or skewed? In this case, if we apply 0, of course the output becomes 0, and if we insert 0, then output becomes 1. That is easy to understand. Then where can you find the crossing point, or what is its input threshold? So you can see that, yes, this is not input threshold, because the condition for input threshold voltage is both of input and output equal to each other. But you know that what is the value here? Do you think that this is corresponding to 0.5? No, it's not. It is slightly higher than 0.5. So I wanted to say that in this transistor or in this CMOS inverter, which one is stronger? P MOSFET is stronger than N MOSFET. Once again, the region shown here is dominated by the strength of N MOSFET, and this upper part or the value equal to high, logical high, is corresponding to the strength of P MOSFET. And you can find that actually the width for P MOSFET dominated by P MOSFET is wider than that of N MOSFET. What does it mean? So from this one, you can understand that in this technology, so we have no idea what it is right now because it is not disclosed right now, but we can understand, although it is drawn here, at least from this voltage transfer curve, we can find that this P MOSFET is even stronger than N MOSFET. So, are you with me? If we have voltage transfer curve, for example, like this, then we would say that, okay, N MOSFET is stronger than P MOSFET. However, in this case, it's not. So why it is so? This is a little different from textbook lessons because we always learn that N MOSFET is always more powerful than P MOSFET when we have same width. But you know, the state-of-the-art device can show the opposite behavior. So we will see what happens for these devices. Okay. So anyway, you can see that this is the voltage transfer curve of inverter is the realistic one, even in the state-of-the-art technology. Okay, so do you have any question? So
스트롱하다는 게 어떤 뜻이에요?
so when I say strong means that when we so simply speaking, I want to say like this. Here, for example, our drain current, if that is N MOSFET, then we can write it down in this way. Gate source voltage minus threshold voltage of N MOSFET and its square. This is the expression for our saturation current. Okay, then so when we say N MOSFET is stronger than P MOSFET, then simply speaking, I want to say that beta M for N MOSFET is larger than P MOSFET. Then when we have the same, same operational condition with different or the opposite polarity, then for given condition, N MOSFET will conduct more current. So that's the way we say N MOSFET is stronger or P MOSFET is stronger. Okay, so please compare your coefficient and what was it? So it is kind of mu n C ox and W over L. Of course, this W is user or designer definable parameter, and also length. Yes, in many cases we can change it, but in logic cases usually we wanted to take the shortest one, so there is a little freedom for us, and with yes we can change it a little. And Cox, this is a really technology parameter, and this is a really technology parameter. So simply speaking, when we compare beta of N MOSFET and P MOSFET, then the freedom given to designer is more or less this width parameter. Of course, we can select device options we have different devices, so high power, low power, something like that, but this is a more high level choice for our transistors.
그럼 두 개가 N이랑 P가 밸런스를 이루는 게 좋나요? 아니면 하나가 더 강하고 약한 게 더 좋나요?
Of course, the answer is they should be matched to each other. So the ideal one is the input threshold voltage should be very close to half VDD. So if it is not, then what will happen? So if let's consider this highly skewed cases. So in this case, in this case, we have very narrow. So it is stuck. So every day we have a little break due to stuck pencil. Okay, now it's gone. Okay, so in this case, although the ideal one would be look like this, and this transition point is corresponding to half VDD, but if we have a severe skew in this case, then is it good or bad for your application? It has high tendency to say that almost everything is just treated as a logical high and input high, and only small portion of our input range can be recognized as input low. So this is not that good. So we wanted to have half and half portion between logical low and high. So obviously we wanted to have well balanced, not skewed, non-skewed IV voltage transfer curve. Okay. So do you have any other question? No?
아까 베타는 베타 그 P를 그냥 똑같이 뭐 카패시턴스나 길이 같은 거 조정해서 똑같이 맞추면 될 것 같은데 그게 어려운 일이
Yes, so let me just restate his question. So he asked me, so well, we wanted to match beta and beta p. So if we are perfectly matched beta and beta p, then we are more probable to have a well-balanced voltage transfer curve. And this one has mu n, Cx, and W over L over course M MOSFET and M MOSFET, and we have a similar expression for this one. So his question was, is it difficult to match beta n and beta p? It's not that difficult. So simply speaking, usually we have, usually Cox of M MOSFET and Cox of P MOSFET, they are the same. So because we are using the same thickness of oxide, and the difference usually comes from this mobility, and in traditional technology, usually electron mobility of silicon is higher than hole mobility of inside the silicon. So what we do is usually we introduce WP, which is larger than width of M MOSFET. Then we can compensate the weak mobility of P MOSFET. That was the situation. So usually we have not to one-to-one ratio between M MOSFET and P MOSFET, but slightly M MOSFET is wider than P MOSFET. But please note that this is not an option for this kind of technology. If we say we wanted to have more P MOSFET or wider P MOSFET, how can you make a wider P MOSFET in this case? Can you make it wider one? Because the width of this transistor will be defined as this width and this width. Sorry about this low resolution and poor poor quality of drawing, but it is not my drawing, but this is drawn by a company. So let me just draw once again. So this is just a side view or slightly tilted view of our transistor, or not transistor but CMOS inverter. But if we draw in this direction, if we have our eye here and just look into this direction, then in reality it looks like this. Here we have silicon and silicon and another silicon, 4 silicon, silicon and silicon. These are for our MOSFET. So now I'm talking about this 3-1, and after that there is some distance. After that we have silicon, another silicon, another silicon, and another silicon. This is a silicon, silicon, and another silicon. These are corresponding to our PMOSFET. So now I wanted to make it double. So I wanted to have a twice wider PMOSFET. Then can I make it? So if I wanted to do that, then one possibility is make it wider. Wow. However, due to the complexity of this kind of production or fabrication, usually we cannot make it in this way because they are coming from the same tall structure. There is one tall structure and they are etched in the same time, and we make this kind of structure. So say that this is wider and this is narrower, that is not that easy to us. So if you are interested with this kind of trick or this kind of technique to fabricate this complicated structure, especially in your case, you can consult to your colleagues because they are really experts on how can we, at least in our simulation, how can we fabricate this kind of complicated devices. Mr. Zhang will be the one you can ask. Okay, so any other question from the students? So anyway, this is a review of our previous lecture 9, and we have studied the schematic of a CMOS inverter that was known, and our previous topic was skewness. So we wanted to have balanced the CMOS inverter, and the skewness comes from the mismatch between NMOS and PMOSFET. So we wanted to match them by design approach. So usually just to tweak the size of our transistors. Okay. Then now let's go to the remaining part of our CMOS inverter. So now we are talking about noise margin. So what is the noise margin? Noise margin means that how much we have some margins for input voltage in our case. So I mean that usually think about this one. This is the axis of input voltage, and input voltage usually have the values starting from 0 ending at VDD. And what we wanted to have is actually in the ideal case there is a happy VDD, for example. Then for this value, the input corresponding to this range is safely regarded as input low, and this happy VDD is safely treated as input high. That is the idealized case, but everybody understands, unfortunately, due to the imperfection of our voltage transfer curve, so usually we have a relatively small range for safe logical L input and relatively small value for logical high value. I mean that in between we have some so-called gray region. So what is it? This is this logical low or logical high? So it is difficult to say. So then we wanted to say what is this area? What is this area? This is the margin for us. So how much we can add some kind of noise signal. So say that in this case the most ideal case is just number 0. Ah, yes. So number 0, if we have Vin equal to 0 volt, then we can provide the best input to our CMOS inverter. But how about this? 0.1 volt. Then is it logical low? Yes, maybe. It should be regarded as a logical low. 0.2, yes, also it should be regarded as logical low. However, now think about two different CMOS inverter. So when things goes well, 0 volt, both of them generate VDD, VDD. Good, but you know the real value of a certain technology or say certain person is revealed when it goes wrong, like 0.2 volt and 0.2 volt. Then let's say that in this case 0.2 volt, this one generate still VDD, and in this case this is not. This is a much degraded value from VDD minus a certain delta. Then which one should be regarded as a better technology or better implementation of your CMOS inverter? Obviously, for given noise value or weak value, we should have a certain margin to recover our desirable output value. So this one is regarded as good situation, and this one is regarded as somewhat unwanted situation. So simply speaking, let's come back to our original axis here. So from this discussion, this width is important, and this when we have wide width for this area, then we say that the transistor so this CMOS inverter is well implemented, and if we have relatively low range for this region, then we would say that it has a small margin and is not that robust against the noisy signal. Okay, so are you with me? So are you all understand so are you all okay about this concept? So this is the concept of noise margin. Why it is called noise margin? Once again, in ideal case, we have only 0 volt over VDD. However, we wanted to ask ourselves how much our CMOS inverter is robust against a small delta added to our input. In this non-ideal case, even in this non-ideal case, our CMOS inverter should work properly. So this is the reason why we call it as noise margin for our noisy signal. So that is one. Then obviously in this case the starting point is quite obvious in this implementation or in this situation, because CMOS inverter always have the nominal value of nominal output of 0 and VDD, and when we consider just a certain width, then we should be able to point out what is the borderline between safe, logical low, and gray region. And what is the borderline between gray region and safe high value? How can you define it? So we just define this borderline as a point with slope minus unity. So here we have certain slope, so round v out over round, so dv out over dv in equal to -1. So simply speaking, beyond this voltage, now we have very steep change of our logical value, output value. So small, small perturbation added in this input voltage will generate a huge difference in our output level. So simply speaking, this is not suitable for stable logic operation. So we must eliminate this range from our consideration. So this point is regarded as the borderline between, safe logical low region and, certain gray region. So this voltage is defined as VIL, and this is corresponding to noise margin for logical low input. Okay, so because we have to find out the distance between this point and that point. However, this value is always 0 for this technology. Only the point over here is important. So let's think about a little bit different technology. Instead of this beautiful graph, let's draw a little bit uglier. If we have this kind of thing, then where would be the input noise margin? So still we wanted to draw -1 slope line. So maybe somewhere here will be the voltage called VIL. Then the noise margin for logical low value will be reduced from original this value to this small value. So are you all with me? So it's not that difficult to understand. And another one is, of course, this is for input low, and also we can think about input high. So of course we have input corresponding to VDD, then output will be exactly 0. There is no ambiguity. However, if we reduce a certain noise value, then we will have a slightly degraded output. So it is not strong 0 or strong logical low. We have a slight output value, but when we consider this kind of a -1 slope line, then this point is treated as a VIH, and the distance between these two numbers, here we have a VDD and here we have a VIH, that is regarded as noise margin for input high value. Okay, so do you have any question on this concept? So noise margin, that is quite important. Then now I will just stop here, and you have your long-awaited homework number 3 eventually. So problem 1, calculate the input noise margin value for ideal IB characteristics. So it means that you can use long channel MOSFET. Of course, you have to use more ideal, more realistic one for practical cases, but this is just a homework problem, so please use long channel IV characteristics, then you can make it. So there is a hint already. So operational points are shown here. MOSFET is in the saturation region and PMOSFET is in the input mode, because linear mode, because you know there is certain ranges like this. We can find many different ones. So if we have extremely low input value, then of course MOSFET itself is completely off. So MOSFET is off, and beyond this threshold voltage of our MOSFET, then now MOSFET is slightly turned on. However, its drain voltage is quite high. Although overdrive voltage is quite small, but drain voltage is too high, it is certain that our PMOSFET is in its saturation mode. On the other hand, in the case of PMOSFET, since the output voltage is so close to VDD, so it is guaranteed that it is operated in the linear region. Then you can have two different modes for MOSFET and PMOSFET respectively. Then you can try to find out the point where you have this condition. It's not that difficult, so please try to do your homework problem. Also, if you have any question, then please let me know. Then this problem 2 is closely related to problem 1, and our problem 1 is related with find out certain expressions. So equation should be found, and using that equation just to evaluate the numeric value for VDD equal to 1.8 and threshold voltage of 0.5 volt. So that's all for our CMOS inverter. And if you have a question, then please interrupt me anytime. Then now let's go to our delay part. So today we want to just start its introduction. So up to now we have thought about voltage transfer curve of CMOS inverter. So right now we can say that, okay, when we apply 0, then we will have VDD, and when we apply VDD, then we will have 0. That is the thing we have studied up to now. However, in reality, we do not apply just 0 or VDD into our system. Instead of this static input, usually what we supply is certain clocked signal. So it is pulsed and it changes between 0 and VDD. Then if everything is quite slow, I mean that let's spend 1 second here, 1 second here, and another 1 second and another 1 second, then what will happen? In this case, we will have 1 second of VDD and 1 second of 0, and once again 1 second of VDD and 1 second of 0. That will be repeated. If we have slow signal, then since our CMOS inverter or any kind of our logic socket is so fast, so then it can treat this slow signal quite well. However, this is not our usual use. For example, it means that this device or this circuit, if we have just 1 Hz or 0.5 Hz signal into it, then it will work perfectly with 0.5 Hz. However, Do you want to have the system operated at 1 Hz? Usually not. What you want to have 1 gigahertz or 2 gigahertz. Sometimes you want to increase it to 2.1, 2.2, 2.3. This small difference sometimes becomes the real advantages of your new device. So think about your new cell phone or new AP for your cell phone. When you think about new technology, then you say that, oh, compared with the previous one, there is a 10% increase of its speed, 20% increase of speed. It's not that drastic between 1 gigahertz and 1 hertz. However, you are really sensitive to 10% or a few percent increase of your operational frequency. So, I mean that our previous discussion up to now with static operation is not sufficient for realistic problem. Usually, we do not provide this kind of slow signal. Instead, we wanted to provide quite fast signal. How fast? As fast as possible. So, what is the upper limit of our operational frequency? What is your opinion? Usually, when you make a certain system, you want to drive your system as fast as possible and say that if this system works at 2.0 gigahertz, then you will say that this is a 2.0 gigahertz system. If you increase it to 2.1, let's say that if it fails, then it will be called as 2.0. However, fortunately, it works with 2.1 gigahertz, then of course your advertisement will be, I made 2.1 gigahertz system. So simply speaking, we drive our circuit to the extreme case, the fastest operational frequency or operation condition, which can be done by our certain circuit. So why I'm talking about this one? So of course, static response is the basic lesson we have to study. However, in reality, we have to consider time-varying, time-dependent, transient response. Okay, so simply speaking, DC or sometimes steady-state analysis means that input is regarded as a constant time-invariant signal, and output will become also time-invariant signal. That is the way we consider this DC analysis. Instead of that, when we consider realistic transient simulation, then or analysis, then we assume that the input signal is a time-varying signal, and as a result, also output is regarded as a time-varying signal. Okay, so do you have any question about this transient response? So please interrupt me anytime if you have any question. Then, of course, then how can you do that? How can we consider this kind of transient responses? So, of course, the final answer for transient response is just to make the chip and just to measure its transient response. That will be the ultimate goal. But please note that designing a circuit or designing a chip takes quite a long time. So say that you have spent several months for designing. After that, when you fab out, and when you tape out, then you send your design to your fab. Then it takes several, once again, months to fab out. then now you get your result and measure the response, transient response. Then it's not very satisfying. Then what you have to do is just redesign. So can you accept this kind of a workflow? Uh, it's not acceptable to all of us. So what we have to do is, before really fabricating our chip, we should be able to predict the transient response of our given circuit. That is really required. So now say that if we have a certain kind of a CMOS inverter, and just by looking at the layout, can you recognize the maximum frequency it can be operated? So certainly not. There is no way to predict its performance without doing some serious job. By just inspection, its layout, it does not reveal anything. So what we do in practice is just solve a set of differential equations, and as a solution of this set of differential equation, then we will get time dependent voltage of your circuit. Then from this information you will treat it as a just representation of a realistic voltage, and you design your circuit to meet certain design criteria. Okay? Usually this kind of job is called as a circuit simulation. So and the representative program for this job is called as SPICE. Although the SPICE was previously a name of a specific program, however, it was so much successful, so nowadays everything having the similar capability with SPICE is now called as just SPICE. So it's like a rental car. So now I'm briefly talk about what is inside our SPICE. Inside our SPICE, then we just solve this kind of equation. So first of all, we define a vector of state variable x. Then what is it? It can be many different things. For example, usually we can have node voltages. So if we have a capacitor and resistor, or once again capacitor or inductor, blah blah blah, then we can here define certain nodes, and these voltages are regarded as entries of this state variable vector x. And if it is related or connected to a capacitor, then we will have this kind of a time differential operator. And if it is related with this resistor, then there will be this current term, conduction term. So maybe you can ask me this question. Okay, professor, now we can find inductor. Then what will happen? Okay, don't worry about that. Even when we have inductor, we can expand this state vector with certain kind of inductor current. Then we can make this, we can recover this kind of form. Then your another question is, these capacitor, resistor or inductor, RLC, they are all passive devices. How about MOSFET, transistors? So still don't worry about that. We can introduce once again still node voltages or source voltage, drain voltage, and gate voltage as entries of this state variable, then this MOSFET IV characteristics can be expressed still the form of this differential equation. So simply speaking, the basic rule is quite simple. First of all, just inspect your circuit and make a large vector containing all kinds of information about your circuit. Usually, the specification can be made by specifying the node voltages in many cases. What is input voltage? What is output voltage? This is more or less your ultimate concern. So just take them as unknown variables. After that, using the properties of connecting elements, so please allow me to draw once again more generalized one. So let me just draw once again, simply speaking. So now think about a certain node shown here. Here we have a certain circuit node, and it is connected by 3 circuit elements. So we have no idea what it is. For example, it can be RLC or MOSFET or any kind of active devices. Also, there can be another circuit elements. Then what we do is, first of all, treat this node voltage as an unknown variable. Then the current flowing this way and current flowing this way and current flowing this way. That for each circuit element it has current conduction. And what I wanted to say is, now you can express this current, let's call it as I1, can be represented as a function of node voltage. So are you with me? Also, if we call it as I2, also it can be written as a function of node voltage. And finally, if we have this third current, and also it can be written as node current. So say all of these branch currents can be expressed as a function of node voltages. After that, we wanted to say that sum of I1, I2, and I3 should be 0. That is basic rule. What is it? This is nothing but just a representation of the restatement of Kirchhoff's current law. At a certain node, sum of all branch current should vanish. That is written here. Simply I wrote KCL. So then, of course, we have multiple nodes. This is not the only node inside our circuit. Of course, there will be another node, and another node. It means that each node can argue their own KCL. Then what will happen? We can collect a set of Kirchhoff's current laws. Then when we solve this set, then that will give us the complete description about our state variables. Okay, so simply speaking, now I'm returning to this slide once again. What is it? This is nothing but collection of Kirchhoff's current law. And what is this X? In many cases, this X vector contains node voltages or inductor currents. Okay, do you have any question?
X에 인덕터 커런트가 들어가게 되면 어떻게 되는 건가요?
Okay, so So his question is, up to now I have said that in many cases vector x contains node voltages, but as an exception sometimes we can introduce uh, inductor current. So his question is, what is the specific form when we include this inductor current? So let me just consider this one. So here we have inductor and here we have a capacitor, and let's say that this is voltage difference V and this is current I. Same happens for voltage and I. When we consider this is inductance L and inductance C. When we consider our capacitor, then we have the relation like this. So if this is taken as our state variable x, then we can say that okay, this is corresponding to rounded over round dtc. So you know that here we have time derivative term. So this is good. However, in the case of our inductor, the governing equation for our inductor is not this way. Instead of that, the voltage is obtained from time derivative of our current, inductor current. So if we still keep only this one as the state variable only, then it is not easy to consider in terms of this first order derivative. This one is unspecified in this case. So in order to eliminate this difficulty, when we have an inductor, we treat also this I as a state variable. Then this state variable is derived with respect to time. So although that is just written as x, but it can consider capacitor voltage and inductor current. Then it can be merged into this unified form. That is my answer to your question. So are you with me? If you have any question, it's okay. So once
그렇게
again,
되면 이제 저 C라는 벡터에도 그 다른 캐패시턴스는 그냥 C로 적힌 게 있는데 인덕터는 그럼 L로 적힌 게
great.
있고 그러면 KCL이 아니지 않나요?
No. So, okay. So first of all, his question or his second question was, then it is no longer this C matrix. When we have just capacitors, then C matrix really contains capacitances. However, when we include inductor current into X value, then this C matrix now does contain the inductance inside it. But why we call it as capacitance? In many cases, we are more interested in capacitive component in this case. So usually we write down in this way. But still, C in general can contain both of capacitance and inductance. And your third question is, wow, when we have this case, if we have this kind of thing, then now this one is no longer KCL. But my answer is no, still it is the form of KCL. Because, you know, how can we make this kind of thing is just we make simple representation of KCL for each node. So please think about it. So this is still KCL all over our cases. Okay? Anyway, that is a really good question, and you know, so there is a name for it. Really good question. Originally, when we consider only node voltages as a unknown state variable, then that is called as nodal analysis. Maybe you have heard about in your electric circuit course. So for sophomore or junior freshman, However, when we include this kind, in general, if we introduce this kind of current component into it, then we call it as modified nodal analysis. So simply speaking, so SPICE inside it, it takes this modified nodal analysis approach. Inside it, it just take node voltage and inductor current as their stated variables. Okay, so really good question. And if you still have a question, then it's okay. Still, you can ask me a question, or you can visit me after this session is over. So this is just a brief introduction about what happens inside your SPICE program. So SPICE program is nothing but just to analyze the netlist. Netlist means that the text format of your circuit schematic, and inside it, it generates this large set of KCLs. Then it solves this equation. Okay. Then now, okay. So in general cases, we can just rely on SPICE simulation. However, if we just rely on everything in SPICE, then we are not that much educated. So although the real world we are using the SPICE, but we just wanted to some definitions and concepts in this lecture. So of course, in reality, you should use SPICE every day. So now we are talking about the delay. So first of all, let's consider the delay. Delay means that what is the meaning of delay in usual case? So there is a certain excitation, and there is always response. So for example, every morning I try to wake up my son and daughter. Hey, wake up! And there is certain response of them. What is their reaction? Oh, please, 5 more minutes or something like that. And eventually, my excitation can be written as wake up, and response is eventually they wake up. So everything, so not everything, but in many cases we can define excitation and response of a system. Then if this time difference is quite short, then what will happen? Then okay, when I say wake up, then they immediately wake up and try to go to school. Good situation. However, everybody understands there is a certain time difference between this excitation and response, and usually that is defined as delay. So now let's come back to our electronic system. Then what is treated as excitation and what is treated as response? Consider, for example, CMOS inverter. Then what is excitation? Previously your input was 0 volt. Then your output voltage is once again VDD. Nothing happened. But now we introduce excitation. Here excitation means that I suddenly increase input value to VDD. Then response should be output voltage should be changed from VDD to 0 volt. However, although I made it quite short immediately, however, in realistic case, there will be certain finite amount of time to be switched from VDD to 0 volt. This is treated as delay. I mean that actually the transition occurs and starting from this excitation and the real change of output, maybe the border between VDD and 0 can be set as, for example, happy VDD. Then when our output value cross the, the border between 0 and VDD, for example, happy VDD, then the time difference between these two cases, that is regarded as delay. That propagation delay in this case. For example, let's have a look at this figure 4.1. Now you can understand this is the input and output, and now input is increased. Okay, in ideal case we can immediately raise up our input, but unfortunately it's not. Even the input case is slowly increasing. Then let's just treat this crossing point, happy VDD crossing point, as start of your excitation. Now you made the excitation. Then the ideal case would be, then now it goes immediately go down. But unfortunately it's not. The realistic response of your system is, okay, there's have certain time delay, and after that the output goes down. Then when it crosses its happy value, happy VDD, then have to have this difference is defined as propagation delay. Why we have propagation in this case? Because it is related with certain logic gate. Here we have a logic gate, and it is related with a certain excitation in input node, and that is appearing in this output node. So we treat it as propagation of information through this logic gate. So that's the reason why we call it as propagation delay here. So of course there is two edges. One edge is logical low to high, and high to low. So we can define propagation delay twice. One is going up and one is going down. So when you're going down and output is going up, and this one can be regarded as another propagation delay. Of course, in general, there is no guarantee that we have perfectly matched propagation delay for rising edge and falling edge. They can be different in general. So of course the ideal case is they should be well balanced and of course minimized. So when we have different values, and sometimes we take average. Okay, and you know that, please understand, there is a confusing concept which is quite confusing with propagation delay. Propagation delay itself is related with the gate probability. So here we have a logic gate, and if we have a slow logic gate, then instead of this relatively fast response, then for example, if we can have this kind of behavior, then what is the propagation delay? Wow, in this case we have quite long propagation delay for this slow gate. So propagation delay is property of a logic gate. Here we have rise time and fall time, and this rise time and fall time is nothing related with this logic gate. I mean that this is property of our pulse. starting from our pulse, we just measure how fast our output is changing from certain value to another value. Certain value is that typically taken from point A to point 2 of a VDD. Why we don't have 1 and 0? Because sometimes it is difficult to achieve the real 1 and real 0. So instead of that, we introduce a small margin for it. So 0.8 and 0.2 are sufficiently close to 0 and 1.0, and it is easy to achieve by many cases. Okay? So, this is my simulation result. So blue, and here we have VDD equal to 1.8, and I just introduce a simple CMOS inverter, and you know that this red line is idealized input voltage, and this green line is simulated output result. Of course, you know that input voltage cannot be perfectly piecewise linear in this case. Of course, we have something a little bit idealized. But anyway, please try to find out certain your lightning propagation delay. So lightning propagation delay is the input is rising. So input is rising and output is now falling. Then what is the point for starting of this excitation? So you can easily understand this point can be regarded as the initial point of your excitation, because your input voltage now becomes your half VDD. Then now you can see that this is the point where your output cross the border between 0 and VDD. So now you can understand, maybe this is the amount of your propagation delay for lightning case. Then please also try to find out the falling case. This is 1 and this is the 1, and you can see that here and there you have distance here. Okay, so simply speaking, in this case, both of your rising propagation delay and falling propagation delay is, so propagation delay is more or less close to 0.1 nanosecond. Because here two interval unit is corresponding to 0.1 nanosecond. So now you can understand the propagation delay of this one. I think that this is really unloaded one, that is corresponding to 0.1 nanosecond. Okay, so now we have transient response of what is it? 1, 2. Now consider the falling edge of an inverter. Falling edge of an inverter means that now, so in this falling edge here, in terms of output, please don't be confused with my falling edge in this case. This is input is rising and output is falling, and in this case input is changed from really immediately changed from 0 to VDD. Even in this case, our output does not change immediately from VDD to 0 volt. Why? It has, so although here we have a PMOSFET that doesn't play any role in this case. So since we have an MOSFET, and now we have just VDD, and it is connected to our output capacitance. Here we have C out, and initially the voltage was VDD. Okay, so are you with me? Because initially input was 0 and output was VDD. So this voltage was initially VDD, and suddenly input voltage is now changed from 0 to VDD, and our MOSFET suffered from this bias condition. What is it? For this MOSFET, it is highly biased, highly driven to VDD, and also drain voltage is VDD. Both of gate voltage and drain voltage are VDD, then certainly it is operated in its saturation mode. Okay, then in its saturation mode, we expect that there is a constant current due to saturation. Then here we have certain charge collected by Q equal to C out times VDD initially, and that is dissipated by our saturation current. So when we have saturation mode, we have a constant current, so the voltage is linearly decreasing. So simply speaking, my answer to this situation is, if I draw red color way, then its output voltage now initially linearly decreasing, because this is a constant. So time derivative of output voltage becomes a constant. However, for linear mode, it is no longer a constant, and we have slightly degraded behavior of charge dissipation. So discharging. So now you have problem number 3 and 4. Please draw the curve. So please draw the curve and do not try to draw with your hands. So please make an accurate curve instead of a schematic one. Please try to draw exact one. After that, once after you draw the exact curve, then please estimate falling propagation delay. So once again, sorry about that. This falling means that in terms of output, and if I follow the definition of our propagation delay shown here, then I would say that this is rising propagation delay. So I will change my slide of following the definition. So we are now saying that please try to find out rising propagation delay of this CMOS inverter. Okay, so sorry about this 3-minute delay or longer lecture. And do you have any question on today's lecture? I want to say that due is next Thursday, because we have oh, am I right? Not Thursday, Tuesday. We have a lecture, normal lectures. Sorry about that. I was confused. So please, October 10 is next. Tuesday. Okay. So I was just confused. Okay. If you don't have any question, then I want to wrap up today's lecture. Thank you for your attention.